basically look at all the Platonic solids, see how many we can group around the shared edge, how much empty space there is, and then we push that one out and push that into a valid 4D corner. The simplest object to start with is the tetrahedron. The tetrahedron has a dihedral angle of 70.5 degrees. We need at least 3 of these tetrahedrals around the edge to make a valid corner. 3, of course, fits very easily. 4 fits. Even 5 fits, but just barely. We just have a few degrees left. And so when we try to fit 5 tetrahedron around this, we just get a little bit bending in 4-dimensional space. And we will need, as we will see, a whole lot of these tetrahedra to make it actually work out. So we can start out with 3 tetrahedra and ask what happens if we forcefully, bend that into a corner. Can we repeat it? And the answer is we will get the simplex, or the 5-cell. So because of the projection, it becomes just a 3-dimensional object, and it loses some of its symmetry. So we have 5 vertices, but the 5th one, to make it as symmetrical as possible, I put here right in the middle. So we get the outer tetrahedron, and then we get the dimples here on each side. They all represent additional 4 tetrahedra, and they don't look very regular, and that's because of the projection. But in 4-dimensional space, all 5 of these tetrahedra are completely regular, and so that's the 5-cell, or the simplex. That's what happens when you take 3 tetrahedra around the shared edge and essentially force out the empty space and bend them into a true 4-dimensional corner. 4 tetrahedra around the corner, we get this object here. Okay, it's called the cross polytope, and it's actually the dual of the hypercube that we've seen before. Okay, so that's the cross polytope, the second regular polytope in 4 dimensions. 5 tetrahedra, put it around the shared edge, you get something that has a lot of tetrahedra. As a matter of fact, this thing has 600 tetrahedra. Most of them are sort of crunched up in the middle here because of the projection, and you just see one giant tetrahedra on the outside, and then adjacent to each faces you see smaller, fairly much flattened out tetrahedra, and you have to just believe me that in there, they're essentially, in addition to this one out here, another 599 tetrahedra. This is called the 600 cell. 6 tetrahedra would exceed the dihedral angle of 360 degrees, and that's like, something warped that is not regular, so that's of no use. We have seen cubes. They have dihedral angles of 90 degrees. 3 of them will fit around an axis, still leave an open gap, and then we fold this one up. We've seen we get the hypercube. If you try to put 4 cubes around the joint axis, you can readily visualize that would readily fill the space without any bending, and so we can tile all of 3-dimensional space with that, but it will never bend and make a regular polytopes in a higher dimension. So we're done with the cubes. The next Platonic solids we may want to try is the octahedron. It has a dihedral angle of 109.5 degrees, so that's less than 120 degrees here, and that means we can indeed fit 3 around a joint edge and still leave a little bit open space, which we can squeeze out and make this then pop into the 4th dimension. And the result is what I believe to be the most beautiful 4-dimensional regular polytope. The 24 cell, made up of 24 octahedra. You can see the outermost octahedron, because I chose that to be, preserved in the projection. But then you see these rather flattened octahedra with one triangle here, another triangle, the small one here, and so a distorted antiprism in between, and then they're more on the inside. I really like this particular object the most because it's not too complex. You can still see what's going on. You can still look on the inside, see the innermost very tiny little octahedron at the center. Now it turns out this object has 1,152 symmetries in 4-dimensional space. And you simply get that by multiplying the symmetries of an octahedron, which are 48, with the number of octahedra, 24. You multiply this out, you get 1,152, because you can take, in 4-dimensional space, any one of the octahedron and put it in place by suitable rotation of any one of the other 24 octahedra in any one of the 48 possible positions. I live at the street address 1152. When I found out that this object has 1152 symmetries, I thought that somehow fate really meant me to be, into geometry. The next one on the list is the dodecahedron, is 116.5 degrees of a dihedral angle. That is still less than 120 degrees, so we can still force 3 of them around an edge and then join them into a valid 4-dimensional corner. It's not bending all that much, and so we will need 120 of those objects in the crust to form a valid 4-dimensional regular polytope. So this is a model of the 120 cell. Of course, you can see the outermost dodecahedron. You can also see kind of this flattened pancake-like, dodecahedron on top here, and each one of the faces has one of those, and then stacked on the inside there are a few more, adding up to a total of 120 of those. We still have the icosahedron. Unfortunately, it has a very shallow dihedral angle. It is more than 120 degrees. It is actually 138 degrees roughly, and so even 3 of them would not fit around this edge without overlapping, and so we cannot form a valid corner, and unfortunately this is useless as far as making a 4-dimensional regular polytope.